kilogram fisherman.
Mass is equal to 85.0 kilograms.
Jumps from a dock into 135.0 kilogram.
That's 135 something. I'm not even gonna change yet, but oh, I'm already there. Okay, sorry. The mass of the rowboat, so with the subscript R, I guess.
R for rowboat.
Yeah, equals 135 kilograms.
We have another mass. What's that one?
Our mass of subscript F or fisherman.
I don't want to use F because that's usually final, right? So
okay, so M. Oh shoot. yeah, M.
M sub M is going to be fine. So M sub M for the fisherman and M sub R for the rowboat.
At rest on the west side.
Stop. So the velocity, the initial of our rowboat is 0.
The velocity of the fisherman is 4.30 meters per second to the west.
Stop. So velocity of F initial, I think,
So the velocity final initial?
is negative 4. Velocity. Yeah, sorry. Shoot. Keep reading.
That's it.
Alright, is negative 4.3 meters per second.
Great. Negative 4.3 meters per second. Negative because you identified and translated from west to negative because west is in the negative direction. Good.
What is the final velocity of the fisherman in the boat?
So V final V final sub F is equals question mark. Sorry, sub F. This question mark in V final sub B or R is equals question mark.
So we're looking for the velocity of the man final and the velocity of the rowboat final. Good. So let me just draw a picture here. We have the lake. We have the dock. We have the guy running on the dock. He's running this way, and he's going to land in the boat, which is right here. Is momentum conserved during this event, Connie?
Yeah.
How do you know, Connie? I do understand that's what we started with this particular day, but it's important to be able to identify why it's true, because there are going to be days where you're not going to know specifically. We're working on conservation of momentum right now. So why is it that momentum is conserved in this particular event? Connor.
Because the velocity initial rowboat is not moving 0.
I agree the initial velocity of the rowboat is 0, but that's not why we know momentum is conserved here. It's important to understand the why before we can move forward. Emma.
It's a collision.
Because it's a collision. Remember, momentum is conserved during all collisions and explosions. This is a collision between the rowboat and the man. So it's as simple as that. So you need to be able to identify anytime you have a collision or explosion, you could say that the sum of the initial momentums equals the sum of the final momentums. The next step, please, Laura.
Take the momentum initial and make it velocity of the man times the mass of the man.
So the mass of the man times the velocity of
the man initial.
Good.
Plus the mass of the rowboat times the velocity initial of the rowboat.
Good. Equals.
The mass, or no, mass of the man times the velocity final of the man.
Plus.
Mass of the rowboat times velocity final of the rowboat.
Okay, good. Spencer.
Oh, well, just all the velocity.
Oh, sure. I can put little vector symbols like over all of the velocities. Stecker, give me all the numbers here from left to right.
Okay. 85 for the mass of the man. For negative 4.3 and plus 135 and then multiplied by 0 and that equals and then max minus 85, and then just velocity, man, final.
We do not know that. Good.
And then plus 135. And we don't know the velocity of the rowboat final.
So there are two things in our one equation that we do not know. Two unknowns and one equation. This, of course, is a problem. Emma.
Well, because he jumps on the rowboat, wouldn't the velocity of the man final and the velocity of the rowboat final be the same?
Notice, because the man and the rowboat are now together, they're moving at the same speed. Therefore, the velocity final of the man and the velocity of the rowboat final are both the same. They both have the same velocity. Great. We can now substitute in 85 times negative 4.3. Rather than having the velocity of the man final and the velocity of the rowboat final, we're just going to have one velocity final. So we can now combine our 85 and 135 and multiply that by velocity final. 85 times negative 4.3. We get that the velocity final equals 85 times negative 4.3 divided by 85 plus 135. So with sig figs, was it negative 4.3 or 4.30? So do we have 3 sig figs?
Yeah.
Okay, so negative 1.66 meters per second, or you could say negative 1.66 meters per second, or I'm sorry, you could say 1.66 meters per second west. Both are acceptable.
Where does the surface that the boat is on come into play? 'Cause if the boat was just on concrete, then the velocity wouldn't be the same, right?
This is an interesting question. One of the things that we were assuming here is that there's no friction between the boat and the water. This would be a very different problem if you were jumping in a boat that was on concrete. You are correct.